Crave the Wave, which is all about physics and wave. And then for the second part, after a break, we're going to talk about Crime Busters, which is about um, chemistry and like solving crimes. Can everyone see my screen?
Not yet, but we can see that you now. We can.
Okay, that's great. All right, we can start now. So Crave the Wave is a Science Olympian Division B event. And you can see on the screenshot on the left, this is taken directly from the Science Olympia website. In this event, competitors must demonstrate knowledge and skills needed to solve problems and questions regarding all types of waves and wave motion. And on the right, there is a much more detailed content list of what is included in the Crave the Wave test. There are a myriad of topics ranging from general wave characteristics to like wave phenomenon Doppler effect. But because of the time constraints I have, I will only talk about general wave characteristics. And I won't talk about like the other harder topics. So every single wave can be basically visualized as an up and down motion. And every single wave has these basic characteristics to them. First of all, every wave has a crest and a trough. A crest is like the upper part of the wave, and the trough is the lower part of the wave. They are very similar. It's just that one's the upper part and one is the lower part. And the distance between two crests, as you can see here from here to here, from one crest to the other crest, sorry. 1 second. From one crest to the other crest is called the wavelength. And the wavelength basically just says how stretchy the wave is. And there is another characteristic of waves called the amplitude. That's like the height of the wave. It's just how high each wave goes. And finally, there are two other characteristics not mentioned in this graph. One is called the period and the other is called the frequency. The period is how long a single wave takes to go up and down. So you can see in this animation here, the amount of time there is needed for one up and down motion to occur, that is a wave. And sorry, 1 second, there is lots of tech difficulties. All right. And the amount of waves that pass through per second is called the frequency. The frequency is very related to the period, as we will see in later slides. Now we can talk about the different types of waves. So there are two main ways we can classify waves. One is longitudinal waves and the other is transverse waves. Longitudinal waves are made of compressions and depressions. You can see that over here, there is a compression, 1 second, in a wave, while over here, there is a depression in the wave. Think of this type of wave as when you try to push against a slinky, where some places are compressed and some places are depressed. Longitudinal waves, even though they look different on paper, they still share every single other characteristic of waves. They also still have an amplitude. They still have crests and troughs. They still have a period. They still have a frequency. And the most common form of a longitudinal wave is a sound wave. When I am speaking to my microphone right now, I am basically compressing and depressing the air between me and the microphone so that I can propagate my sound waves to my microphone. And the other type of wave is a transverse wave. And this is a wave that you are probably most familiar with. It's the common up and down motion that you see in graphs and charts. And these waves is what compose light waves, ocean waves, etc. And there is technically also a third type of wave called a torsional wave. And the torsional wave is this twisting motion that you see on this animation here. It's very rare because it's actually really hard to produce, but it has a really high importance in architecture because this type of wave is actually the most destructive waves for buildings. One famous incident that you can see here is one type of wave you can see here is the torsional wave on this bridge. This is called the Tacoma Bridge, I think. And because of wind, it started having these torsional motions that eventually caused the bridge to get destroyed by the wind. And oh yeah, there is a third type of way you can classify waves. You can classify waves waves can either be mechanical or electromagnetic waves. Mechanical waves, as you can see here, require a medium like air or water. When I am speaking to you, my sound waves require air in order to transport because it needs that air to compress and depress. But however, electromagnetic waves such as light don't require a medium. This is how we can see planets such as Mars through space. Even though space has nothing, it is a complete vacuum, light can still pass through because electromagnetic waves do not require a medium. Similarly, mechanical waves must need a medium, right? So you cannot talk in space. Sound waves cannot pass through to space. So if you watch movies such as Star Wars, you technically cannot hear any of the any sound in space because mechanical waves require a medium. And I would like to add one more thing about electromagnetic waves. Electromagnetic waves are made of a magnetic field and an electrical field. When you have a magnetic field propagating with an electric field in 90-degree angles, then you get this electromagnetic wave. And electromagnetic waves are what composes light. And there are much more other types of waves, such as gravitational waves and like plasma waves, but they are extremely uncommon. So usually people just focus on the mechanical waves or the electromagnetic waves. And I said today how I was only going to focus on waves and nothing else. So I'm going to go much deeper into the different formulas and calculations behind wave motion. So probably the simplest formula is the frequency formula. I said before that, one second, let me get some people out of the waiting room. So I said before that frequency and period are related. This is because, as you can see here, frequency is really just the inverse of time, while time is the amount of time it takes for a single wave to occur. Frequency is the amount of waves that a single unit of time, amount of waves that pass through in a single unit of time. They are just two opposites of each other. So if you know the period of the wave, period of a wave, for example, you can calculate frequency with this formula. And you can also calculate the velocity of a wave using its frequency and its wavelength. Many people may know the speed of sound or the speed of light, but many people don't actually know how those speeds are actually calculated. The formula is speed is equal to frequency times wavelength. This funny symbol you see on the right, that's lambda, which is the Greek letter, and it stands for wavelength, which, as you recall, is a distance from one crest to another crest of the wave. If we know the frequency and wavelength of a wave, then we can find out the wave's velocity. For example, if we have ocean waves and we want to see how fast a surfer will go on that ocean wave, then we can find the frequency of that ocean wave. We can figure out how many waves, ocean waves pass through per a single second, and we can find the wavelength of the wave, which is how long that ocean wave spans. And using those two pieces of information, we can figure out how fast a surfer can go on an ocean wave. And here we have a derivation of how we figured out this equation. So we all know that velocity is distance over time. Well, we know that wavelength is the amount of distance a single wave can span, right? And we know that frequency is the amount of waves that pass through per 1 unit time. So we can use unit analysis to find out that when we multiply distance per wave to wave per time, we can cancel out the two waves and get distance over time. And that's how scientists figure out this velocity equation. So remember, velocity of a wave can be calculated through multiplying wavelength and frequency. So I want everyone here to try a practice problem. So say we have a vacuum where the wavelength of light is 5.12 times 10 to the negative 7 meters. And we know that the frequency of light is 5.86 times 10 to the 15 hertz. Hertz is just another, hertz is a unit of frequency. So using those two pieces of information, what is the velocity of light? And I have the equation over here for your reference. Everyone can try this practice problem out. I'll give a few minutes. Oh yeah, and if you have an answer, you can just tell me in chat. All right, I am getting a few answers here. I see some correct answers, but those correct answers are rounding way too much. Try to keep it as precise as possible. I'm seeing people that are rounding 5.12 times 5.86 to 25. Try using a real calculator and getting a much more precise answer. Okay, I'm just gonna stop now and talk about the answer. Um, okay, so there was actually a typo in the question, but it doesn't really matter. So I'm looking at everyone's answers, and everyone has I'm very impressed that everyone has the same reasoning to how they got their answers. So yes, you just multiply these two values together to get the velocity of light. Now, I actually got this question from Google, and they actually got the wavelength of light wrong. The real wavelength of light is 5.12 times 10 to the negative 8. But uh, if you do multiply these two values together, then the final answer should be somewhere around 3 times 10 to the 9 meters per second. But if you correct this value to 10 times 10 to the negative 8, then the real answer is 3 times 10 to the 8 meters per second. And this is the real speed of light. The real speed of light is approximately 3 times 10 to the 8 meters per second. And yes, that is how scientists figure out the speed of light. And yeah, sorry for the typo too. And there are many other factors other than wavelength and frequency that can affect wave speed. I got the screenshot from Khan Academy. So the first factor that can affect wave speed is the wave type. A classic example of this is how you hear lightning before thunder. I mean, you see lightning before you hear thunder. Lightning and thunder are both forms of waves, but lightning is a electromagnetic wave. It is a light wave that travels very, very fast. As we calculated in the previous example, it goes at 3 times 10 to the 8 meters per second, which is unbelievably fast. But thunder is a type of sound wave. It's a mechanical wave that has to travel through air, which is much slower than light. So because of the different wave types, electromagnetic waves travel faster than sound waves and therefore have a higher velocity. The second factor is medium. A medium is basically any type of substance in which a wave can go through. For example, air is a medium for sound. Uh, metal can also be a medium for sound, as long as it is a type of material that can transport wave energy from one place to another. It is a type of medium. And in the next slide, I'll focus more on how we can calculate a new wave speed when we know the medium. So this is just going more in depth into how medium can affect the velocity of a wave. So here we see different mediums affecting the speed of sound. For example, air has a much slower speed of sound than water because they are two different mediums. A sound going through water is much slower than sound going through glass because they also are different mediums. And you can see that the more solid the medium is, the faster sound goes through it. Like how air is a gas and sound goes very slowly in it, but aluminum is a hard metal and sound goes very, very quickly in it. You can also see how temperature changes the speed of sound. Temperature is also a property of the medium. And when the temperature of the medium changes, the speed of the wave also changes. Same goes for the speed of light. The speed of light in air is probably the quickest, but the speed of light in diamonds are much slower, almost more than half slower than light going through air. And this is also because of the different mediums. Here we see a contrast to sound. For sound, it goes faster in solid substances, but for light, it goes slower in solid substances. And how fast a wave can go through a medium, and here we're talking specifically about light wave, is the refractive index, and it is denoted by the symbol n. The larger the n value, the slower light goes through it. So light goes very, very slowly in diamond, and therefore diamond has a very high refractive index, while light goes very, very quickly in air, so it has a lower refractive index. The closer the refractive index is to 1, the faster the speed of light goes. The speed of light in a vacuum is the fastest light can ever go. So the speed of light in a vacuum is defined as what the refractive index of the speed of light in a vacuum is 1 for that reason. And here we have an equation for calculating the refractive index. C is the speed of light. And you can recognize this variable from the very famous equation E equals mc squared. So c is the speed of light, and velocity is the speed of light after going through the medium. When the velocity of the actual velocity of light is slower than the perfect velocity of light in a vacuum, then that means it must be going through some sort of medium. And we can calculate the refractive index of the medium through this equation. So say we want to find the speed of light in a diamond. Well, we know the refractive index and we know the speed of light in a vacuum. So using the equation n equals c over v, we can calculate the velocity of light in a diamond. Oh, so everyone try to use that equation to find out the speed of light in a diamond. Oh yeah, the equation. Okay, the equation's on the screen. So we're trying to find the speed of light in a diamond. All right, I already see some correct answers. Uh oh, oh yeah, sorry, I forgot to put c. C is the speed of light, and it is I'll put it in chat. 3 times 10 to the 8th power. Yes, v is velocity. All right, great. I'm seeing lots of correct answers here, which is great. So yes, the final answer is 1.24 times 10 to the 8th meters per second. So you can see here that diamond really slows down the speed of light. It slows it down by more than half. So even though diamond seems to be clear and shiny, it really slows down the speed of light more than water and any other substance. And the reason why diamond speeds down light so much is because the molecular structure of diamond is really compact. So it becomes a really big wall for a light to go through. Can an electron go faster than light in a diamond? I don't think so. Diamond number 1 slows down light, and number 2, I'm pretty sure nothing can go faster than the speed of light. Oh, never mind. So we got 2 equations for finding the velocity of light, we got number one, velocity equals lambda times frequency, which means it equals wavelength times frequency. And we also got that the velocity equals the speed of light divided by the refractive index. So we can equate these two equations together. We can say that lambda times frequency is equal to the speed of light divided by the refractive index. Well, say say a diamond slows down light, then this part over here, lambda times frequency, must also decrease because c over n also decreased. So if lambda times frequency decreased, then which equation actually, which variable had to go down in order to facilitate that decrease? Did the wavelength decrease in order to slow down light, or does the frequency decrease in order to slow down light? Well, the answer is that frequency never changes even when going through different mediums. This is because frequency is what dictates the color of the light. Each color within the visual spectrum has its own set frequency. Red light has a lower frequency, while blue light has a higher frequency. And so we cannot change frequency because going through a medium does not change color. When you shine a beam of light through a diamond, that diamond, the light that comes out does not change color. However, wavelength decreases when you shine a light into a diamond. Wavelength does not change the color of light. So even if you decrease wavelength, it does not change the color. It only changes the speed of light. Okay, and now I think we can start a Kahoot now. This Kahoot has lots of hard questions that I would like to go through. So Andrew, can you start the Kahoot? Um, hello, Andrew? Okay, I don't think he's responding right now. Let me try it myself. To whoever just asked what we are doing, we're trying to create a Kahoot, we're trying to do a Kahoot right now, and I'm getting it set up right now. Oh, that's right.
Can you send the link?
And Andrew, can you like stop the Kahoot like at like when we're transitioning from each question so that I can explain it? Right. we might go a bit later than schedule. So we might end like around 4:45, but I think it should be fine.
Tell me when to start.
Oh, yeah. All right, I'll give like 30 more seconds for people to like finish joining, and I'll start it. All right, let's start it.
Start.
Yeah, you can start it.
Give me a sec. Let's go.
All right, so remember the inverse relation that period had with frequency. Frequency is equal to 1 over the period, and therefore they are related. All right, we can go on to the next question. Oh, I misspelled waves. All right, so remember transverse waves are the stereotypical waves that you'll imagine. They're the up and down motion that you see on graphs. But sound waves are not up and down motions. You cannot transport sound through air merely by doing up and down motions. You can only compress and depress air. And that type of wave where you compress and depress is longitudinal wave. And I don't know what a surface wave is. I just put it there for fun.
Oceanography is a dynamic planet reference.
Oh, my bad. This should be an easy one. Oh, never mind then. If I didn't make this clear enough, electromagnetic waves are the equivalent of light. Because all light is just some part of the electromagnetic spectrum. However, remember how I said that electromagnetic waves, unlike mechanical waves, do not require a medium to propagate. That's why you can see light in space despite space being an absolute vacuum, but you cannot hear sounds or do any other mechanical wave in space because there is no medium. Now, light can still travel through mediums. That's why we have that equation for calculating the new speed of light through a different medium. It's just that light can still travel without a medium. Oh yeah, get a calculator for the next few questions because we'll be doing some calculations.
I don't have a calculator.
Oh, you don't have a calculator.
If you're on
Use
Mac, press
Google.
Command Space Calculator.
You can open
I'm
Google.
on Windows.
Just use Google, guys.
Well, then I'll have to switch back and forth.
Just put it over the Zoom screen because the questions are on your end.
All right, these may be a bit hard, but remember that hertz, the symbol is just the unit for frequency. And remember the equation V equals lambda F. And Andrew, there is a lot of time on this question, but once we get to like a good amount of answers, you can just skip it.
All right. How many people
Wait,
joined,
just
by the
give
way?
a bit more time because some people may be still writing it, but if you
Yeah.
feel like there's enough, then
Yep.
I think it should be enough now. We have like 31 people, right? Ooh, that's great. To whoever said 8.2 nanometers, sound waves do not go onto the nanoscale. They usually are on like the centimeter scale or the meter scale. And if you really want to calculate this out, remember the equation V equals lambda F. Well, we can change the equation into lambda wavelength equals V over F. And when you divide 353.4 meters per second by 100 hertz, then you get 3.5 meters. So for this question, just think about what other variable is related to frequency. Yeah, let's skip it for the sake of time. That should be enough answers. Oh, a very equally distributed answer. So remember in like a previous Kahoot question, we talked about the relationship between frequency and period. Frequency is 1 over period, so period therefore is also 1 over frequency. So if you do 1 over 150, you get 0.00667 seconds. Frequency has nothing to do at all with wavelength. Since we didn't specify that speed here is conserved, we cannot assume that the equation V equals lambda F actually can work. So we can only assume that the period, we can only find out the period. Oh, this is a hard question. I think I made it too hard. Guys, don't guess. Actually do this question. I already see
Hello?
11 answers.
How do you do it though?
Yeah, I think I made it too hard.
If it's too hard, then people are just gonna guess.
Is it
Yeah, but-
45%?
Bro, he can't tell you or else everybody will like.
This was an actual Crave the Wave question, by the way. Just to give you more motivation.
Oh my god, I actually misclicked.
Bro, imagine you misclick and you get it right.
But I know
Bruh.
the thing I misclicked on was not the right one.
Well, oof.
Y'all are like elementary schoolers, it's fine. I'm a high schooler. But like this question is definitely easier than like one of your AMC8 questions. AMC8. Okay, Andrew, can I share my screen after this to talk about how to solve this question?
Sure. Well, this is the last question, so I'm just gonna
Yeah.
podium time. It's podium time. Who wins?
Alex, Daniel, and Oliver. Good job.
Yeah.
All right, I'll share my screen to. All right, this question. So we want to find the percentage of velocity that is lost, right? So we can find the amount of velocity that was lost through this symbol delta V, which stands for the change in velocity. The change in velocity is the equivalent of the amount of velocity that is quote unquote lost. And to find the percentage, what we do is we put the change in velocity delta V here over the total initial velocity, which is the velocity of the water, or VW. Now we can keep expanding this. The change in velocity is just the speed of water, the speed of light in water, just subtracted by the speed of light in a diamond. And we keep simplifying this, and we expand it so that we divide the fraction into two parts. And we can simplify the VW over VW into 1. So we're really just left with VD, the speed of light in diamond, over VW, the speed of light in water. And when we keep on expanding that, we get C over 2.42. Remember the equation that we learned of how V is equal to C over N. We can plug N in for the diamond and the water, and the two C's cancel out. So we eventually get 45% decrease in the amount of percentage 45% decrease in the speed. And this is really similar to like the question we did previously on the diamond. You can see that the diamond really decreases the initial speed of light, which is impressive. And I'm just gonna give like 5 minutes of break, even though we skipped the entire break time. So come back here at 4:55 and we can talk about Crime Busters.